Okay. Hello everyone, good afternoon. Uh, okay. So I would like to uh, finish off what we have yesterday. That is the vector functions. So the chapter 12 and chapter 13, the vectors and vector functions, serve as I would like to say it's like additional chapters to set up uh, your previously your calculus 1 is about the single variable calculus, and now calculus 2 is actually we call it a multi-variable calculus, which is we are going to see that the descriptions is not only on one single variable. Usually we say the variable x, then we say function of x, and etc. But now we are going to see that we are going to develop in more variables. The functions will be in terms of variable, at least 2 or 3 variable, and simply the transitions to see the increase of variable is through the vectors. Okay, so we say that we could take the R as a vector functions, okay, and the f of t, g of t, and h of t, all of are real functions, okay, and based on the variable or parameter t. Okay, so based on this definition, if you look at the curve like this, we can think the r is actually the positions. We can say its positions if we vary our t, let's say from 0 or maybe from negative something, and then we could trace the curve through these vector positions. Okay. Now the same way apply. We try to trace this r. Okay. When you try to trace this cosine t I sine tj plus tk, which means that we are going to trace for every possible value of t. Okay. So for example, we start by looking at this. Okay. So simply, this is just saying that, let's say we start from r0, like for this point here, 1, 0, 0. So if you plug in t equals 0, this is what positions that would be. So basically, what we are doing here is basically we set up r0 like that, okay, and then you take for this part here, which is this is t for equal pi over 2, okay. And that's pi over 2. And then the same way, you trace for all possible t, for all this values of the vector functions, and we get that this is going to be its movement. And so we trace within this red curve, like in the space curve. Okay, we call that our space curve. Okay. Okay. So I hope you get the logic behind it. So we continue now to get the derivative. Okay. So this is just some notes. Okay. So now we get through the derivatives and integrals or of vector functions. So we say the definition of the derivative. Let me write directly. The r dt is basically what we say the r prime t, or we say if we take the limit as our definitions. Hope still remember this as well. So limit. So this is the functions, and we change the function with r. Okay, so r t plus h and minus r t over h. Okay. So this is pretty much the same definition as we did in calculus 1, but we changed the regular functions with the vector functions. Okay. just make it clear here. So if you see on this picture now, so this is pretty much how it looks like. If we take the positions t plus h from the origin of t, so we know that this line is our secant line, or now it's secant vector because now it's secant vectors. But in our travels one, we say that it's the secant line, and here is the tangent. The tangent. So the tangent, we say that if we take this, the movement as plus h for original positions, now we say that this part here is the tangent. You can imagine that this is going to be the differences on the r, the t plus h and t. So it's the h identified by h. And so based on our limit definitions, as we take the h getting closer to 0, which means that if we take this point Q and take closer to P, okay, it is practically the same as calculus 1. We say that this is the definition of the derivative. That's why we get that this is our tangent. This is our tangent, or the tangent vector. It's precisely tangentially for this point P. Okay? So tangent vector are prime at P. Or we can say the tangent is a tangent line to C at P. We can say it's defined to be line through P that parallel to tangent vector r prime t. Well, basically we could say that that's also our tangent line, but it could be defined with more general descriptions that is actually a line that is parallel to tangent vector r prime t, which means that the gradient, or if you get the gradient in this 3D system, is the same. Okay? The tangent is the same. Then and since we are in the world of vectors, then the terms unit vector also apply within this case. Okay, so we can say the unit tangent vector, let's say t, is defined as what is unit vector? Unit vector is, it has the same direction as the tangent vector. Okay. This is the definition. Okay. So this is limit definition of the derivative. Okay, and so based on the definitions, we can say that if we have R with component f, g, and h as each of them as a function of t, then we can say that the derivative of the vector function R is basically the derivative of each component. So it's I think quite intuitive and I think quite understandable. And then this is some proof for each part, and I think it is very intuitive. So we say that we are able to take the plus some additional small distance, the h or delta t now, and we take the delta t to be 0, and then basically we say that we are break down all these component into f, g, and h. So we take all, change to t plus delta t, and divide by delta t, and that is basically the definition for each function's derivative, right? So we can say that we can take the derivative for each component. So if you are asked to find the derivative of the vector functions, meaning that each component you just need to take the derivative of each one, okay? Each one of them. So for example, if you have R is 3t squared I plus te minus tj plus sine 2tk. And you want to know the derivative. So basically we are going to take derivative for each part of the components. So take derivative for this I, it's for x-axis. This will be 6t, right? And this will be plus derivative of this is, we're going to take the chain rule, right? Don't forget the chain rule. So we're going to take e negative t minus t e negative t, right? So we get 1 minus t e negative t, right? And then plus 2 cosine 2t. Okay. Okay, and then after we get this definitions and theorem, then there are another property that probably helpful in terms of vector functions. Some of it is the same as we did in calculus 1, but but another one is, I think, quite new and I think important also as well. So you can see from this theorem, suppose that u and v, they are vector function differentiable, and then c is a scalar, f is real functions, real valued functions, then you can have all this property. Okay. So if you want to derive in addition equations, then you can take derivative for each of them, right? So you can see that some part of it using the chain rule, okay, and some part of it I think quite important and interesting is number 4 and 5 actually. So if we take the dot or cross product, then we are going to take each one of them based on how we treat them as in chain rule. Okay. So if you take the u dot v like this, then you take u prime v plus u dot v prime. So let's take like a product rule. I'm going to write here, maybe similar to product rule. Right here, product rule. And then the last one using the chain rule. Just a quick notes on the number 4, this one here. If you want to look at into more detail, so if we take this, okay, let's say we have u and v with different functions inside. Okay. First, we take the dot product for both of this u and v. Okay. And we can write in the summations, okay, f t g t, and then 3 times n1, n2, and n3, right? And then if we take the derivative of u dot v, means that we are going to derive the summations. Okay. So derive the summations means that we derive this, and then we take the product rule, right? The product rule from here, and that's why we have this part, and then we can take this each one of them, and that's why we can say this part here is actually u prime v and u v prime, or u prime dot v, u dot v prime. Okay, I think not really that complicated, the proof. Okay. And it's quite intuitive. And then also another theorem that is important as well is this orthogonality for the R prime. Okay. So I think, let me put here. So if we take for any vector positions or any RT, if we take this, the R prime is always orthogonal to the R. Okay? And we can also prove this using the idea that so RT dot RT is the scalar, right? It has the value C. Okay? And then we take derivative of this R and simply we get this one here, and we simply get these equations, and we get that at the end of the day we get 2r prime t dot rt, okay, from this derivative. Okay, so by this theorem, okay, so basically we say that I think it came from this. So if this is going to be C and the whole thing is derived, okay, this part here on the left will be 2 r prime t dot rt, as you can see from this one here, and then the constant has become 0. Okay, so that's why we say that this is equal to 0. Or if you want to visualize this orthogonality, you can also look at this two functions, vector function here that is going to have 90 degree, right? Remember that you have the dot product that is going to equal cos theta, right? And here the cos theta here is 90 degree, right? Which means that this will be 0 if both of them are orthogonal. Okay, so we can see this as well, or we can see from this proof from the calculus part. Okay, so that's all for the derivatives. Okay. Okay. We'll wait for a couple minutes. So to calculate the r dot r or u dot v, um, you can view this in two methods. Okay, you can dot the product first and derive, or you can derive first and dot the product. Okay, the same result should be the same result. So it's up to you how to calculate the method. And if you want to have an example here, let's say we have R1 is 2ti plus 3t squared j plus t cubed k. And let's say R2 is t with power of 4 k. Okay, just that. And we want to know, compute ddt of R1 dot R2. Okay, so first we can take the dot product first. Okay, so let's say we take, let's say this is ddt, and then we take the dot product, which is, I will just draw this 2t, 3t squared, and t cubed, and then dot. This will be 0, 0, and t with power 4, right? And then we get that this will be let me just write directly. So we have 0, 0, and t with power of 7, right? Or maybe let me write 0, 0, and t with power of 7. And at the end, or this is already t power 7. And then this will be 7t with power of 6, okay? Or we can derive each one of them, like in our method in the formula. So let's say this is R1 dot R2. This can be R1 prime R2 plus R2 or R1 R2 prime, or R2 prime R1 is the same. And this will be dot product, both of them. Okay. So we derive first and take 60 3t squared, right? And then dot with 0, 0, t with power of 4, and then plus 2t, 3t squared, t cubed, dot. The derivative will be 0, 0, and 4t cubed. It's quite long, but if you see from what we have, this will be 0, right? This will be 0. So we have 3t power of 6, right? 3t power of 6. And this will be 0, 0, and we have 4t power of 6. So 4 plus 3 is 7. So the same result with this, right? So either way is the same result. Okay, so you can take the dot product first and derive, or you can directly write the r prime r, or u prime v and v prime u. So whenever you have a dot product or cross product, okay, you can have two alternative approach. Okay, you can first take the dot or cross product, check the result, and then derive, or you go for this formula and then derive within the product rule, like a product rule. If the question is as simple as this one, I prefer dot product first and then derive. I think much more manageable. Okay. Okay, now let's move on to, I think we can erase this one and then we move to this one here. So now is the integral. So integrals. So basically, similar with the derivatives, we can also view the integrals of vector functions as integration of each component in that vector functions, right? So as introductions, you can see that definition for integral, which is a limit as n going to be infinity of the summation of the r vector function r with some t delta t. Okay, if you remember that this is going to be in calculus 1, we see that this is going to be the rectangle, right? The rectangle, but now this is on the vector functions. Okay? And take each component f, g, and h, and we see that they are all the definition of the integral itself. So we can rewrite the vector position or vector functions integrations by take the integrations for each component. Okay. We can also rewrite these integrations if we remember the fundamental theorem of calculus. We can take this in terms of antiderivative. Okay, let me write the capital R. That is going to be RB minus RA. And R is, this capital R is antiderivative of the vector functions. So we can also write that if you take derivative for this R, this is actually the vector function itself. And then this is the same if we take the indefinite integrals, okay, without the value. And that's it for derivative and integral. Okay. Okay, we have derivative, we have integral. The next part is the arc length. The arc length. So before we have the exam, the final exam, perhaps we are going to have a quiz. But I think, as I see the schedule, I think the quiz will be just like online quiz. So you can serve that as a practice so for you, but that will be a quiz. Maybe in next 2 weeks. Okay, next 2 weeks. But the chapters is on vectors and vector functions. So we still have time for to finish off the chapter 13, this vector functions, and having some maybe practice. Okay. And then yeah, I think we can still have a little bit more time for practice. And then we can have the quiz. Okay. The quiz, you can open your notes, you can use all the things you have, you can use calculators. And hopefully you can have much more experience during the test. Okay, the arc length, if you remember the arc length, let me just make some quick review on what is arc length. So we say that we have the curve. Let's say we just did this in chapter 8, right? We have y and x, let's say. So the arc length is actually how we measure this curve, right? We measure this curve. Let's say this is a function of x. So we want to measure how long the function is, right? How to measure, what is the measurement? So I'm usually taking the definition for the arc length is taking some part of the length. Let's say we take this part here. Let's say this is the tangent, right? The tangent. And we say that this is going to be dl. And as usual, the other part will be dy, dx, okay, according to each axis. And then we can take the Pythagorean. We can take the Pythagorean, right? And then we can derive that this is going to be L is integrations. So we 1 plus dy dx squared dx, right? From A to B. Let's say this is A, this is B. Okay. And then in chapter 10, we also have in parametric, that is if x is function of t, y also function of t, then we can have the L is from A to B. We have each one of them derived by t, right? Okay. Now measuring the same method. This is if we have an illustration for how to measure the curve. So let's say we have this, the blue curve, and we are going to be approached by this red line. Okay. This red line serves as a small distance in between of points inside the curve, right? So similarly, at the end of the day, we are going to have very similar to what we have in parametric, but we are going to have in z. Okay, so x, y, and z. So we can say that this will be f prime t, t prime t, and h prime t. So this is if, okay, maybe let me write, it's going to be that way, this is going to be this way, maybe this one will get bigger. So vector equations, let's say we have ft, gt, ht, and t is from A to B. So we can say x of is ft, y is gt, and z is ht. They are all parametric equations. And we can say f prime, g prime, h prime, they are all continuous, okay? So that we can continue to write down this formula. So this is the formula for the arc length. If the curve traverses exactly once. Okay. Because if you're not careful, because the parametric can have loop, right? And it can be like circling around, like maybe in polar. So sometimes we need to make sure that the distance or the t, the variable t, is making the measurement just once, okay, one time. Okay. If this is like circling around, then we need to cut where it is not going to be twice, okay, or more than once. Okay. So we need to make sure that this A and B is exactly traversed once. Okay, now this can be simplified. Okay, let me write first. This is going to be, we can take, this is dx dt squared, dy dt squared, dz dt squared, and then dt. Now this calculations, these equations, the squared form of this all component of the vectors is the magnitude value of the vector itself. So we can simplify this and makes, so it's magnitude of the r prime. Let me take notes here that the magnitude for r prime is basically ft f prime t squared plus g prime t squared plus okay, let's continue. Okay, this is the conclusions, the arc length. And now, aside from arc length, we also have the arc length functions, which if we want to um, take the arc length into more segmented parts, okay? So if we take the functions, we can write like the s as arc length functions. The variable is t, which means that we are going to take a segmented part of the curve, of the length of the curve, and then we can take the variable as its end point, okay? And then we need another variable to make this integration works. So I will take the variable u. Okay, so we can write, this is the magnitude of the r prime u du, okay? And then we can write this and then just break down everything. So this will be dx du. So we can take ds dt as r prime t, okay, by the fundamental theorem of calculus. So this is what we call the arc length functions. So what we are doing here is actually we parameterize into another variable. Okay. So for now, if we see that this is going to have t as a variable for the functions, then we need to reparameterize u. Okay. Okay, just slide notes for the arc length functions. So I think the next one will be the core on the chapter 13, which is the curvature. Curvature. So let me wait for a couple of minutes. Okay, now let's see the curvature. Okay, let's say this is a curve, okay, curve C, and then the red color means that it is the tangent, okay, the tangent for each point on the curve C. They are all unit tangent vectors. Okay. So, as in definitions, if to get into the curvature means it describes how smooth the curve is. So you can imagine smooth means that if we have like maybe this and maybe this, you can see that they are different in terms of roughness, right? In terms of smooth. So we can say that the curve or the curvature This is the symbols for the curvature. So the curvature, it symbolizes or it describes how rapid the curve is changing with respect to the length. So the curve is changing. We know the curve is changing through this red line, right? But to know whether it is smooth or not, we need to take the ratio between this tangent and its length. Okay. So we can define and write the formula. The basis for the curvature is the ratio between dt and ds. Where t is unit tangent vector. Oh, I think I read it right here. But these expressions is not easy to compute. Okay, dt/ds, the magnitude value of dt over ds is not easy to compute. Okay. Because ds itself is specific to the arc length, right? So we need to get into this equation and break down this equation into more simplified so that we can calculate more easily. We can write first from our notes that dt over ds, we can write in terms, if we take the chain rule with respect to dt, we get that this is dt over small t, which means this is the derivative with respect to t of the unit tangent vector. So we can write dt over ds, this curvature, as dt over dt like that, or maybe do it right. dt now both will be a derivative, right? Both will be derivative. The first one derivative of the unit tangent vector. The second one is derivative of the r prime, right? Remember from the arc length, we have this r prime, right? The magnitude value. Or we can write into more should be this, and this. This is the conclusions. Okay, for using these expressions, let's say we have an example that we have the R, and this is going to be a circle. Just take these two axes, this x and y, for the vector positions. If you want to find the curvature, so first we need to take the derivative. So cosine becomes negative sine, and then sine becomes cosine. Okay, and then we take the magnitude value of this derivative. So it's sine squared plus cosine squared is 1. So we say that this is going to be a squared, it's a, right? So we can say this a. And then take the unit tangent vector. This is going to be r prime t. Define its magnitude value. So basically this is going to be a cos sine t I plus negative sine t, and then cosine t j divided by a. This will be negative sine ti plus cosine tj. So we take the derivative of that unit tangent factor, so we get negative cos ti plus, or now it's negative, and this gives the magnitude is 1, right? So take the curvature. This is maybe let me write here. So the curvature is magnitude of the derivative of unit tangent vector divided by r prime. So this will be 1 over a. So the curvature for a circle is 1 over a. So it means that if we have a circle with radius a, the curvature is 1 over a. So if we take a small circle and we can take a bigger one, the small circle, this will have large curvature, and the bigger one will have a smaller curvature. This is because the curvature at the end of the day for the circle is 1 over the r. And since r2 is greater than r1, so we can say the K1 is bigger than K2. The curvature 1 is bigger than curvature 2. If you want to make more visualizations through these two circles, you can see that this small circle is changing faster than the bigger one, right? Okay, I hope you get the visualization. You can take maybe a point here. You have the unit tangent factor there. So the tangent over there, right? And here, it takes much more distance. So we say the ratio, this one having bigger curvature. Okay, now another theorem that can hopefully can help is this another form of the curvature, which we have here is the r prime cross the r double prime, defined by r prime by taking the power of q. Okay. So for proving this part is really long, so I think I will just give you some additional information later. But this basically start from taking the r prime t and take the cross product. Okay, so you have some sort of long equations here, and then you need to simplify the form and using all the property for this two vectors. Okay? So if you see the cross and you see that, you can assume if it is orthogonal what will happen, and you can simplify the forms, and at the end of the day you will get that this will be equaling to this. Okay? Okay, so this curve or the curvature, it is used to take into the space curve or the regular vector functions. What will happen if we take just a functions that is just one variable like f of x? We can still also using this same formula for this one as well. So let's say if we take for case for y equal f of x. Okay. So first we take the r with a function of x. So for the x-axis, we say that this will be the variable x, okay, for the I. And for y, because it's a function of x, then we say that this is function of x, j. So this is our vector function. So first we define this. We take the r prime. So this will be I, and then this will be f prime x. Okay, and then this is going to take the second derivative. This will be 0, the x part, and the j will be f double prime x, and then j. Okay. Now taking the r prime x cross r double prime x, okay, you will see that if we take this two, we go right here. So I, j, this is 1, prime x, this is 0, this is f double prime. you'll see at the end of the day, this will be just f double prime, but in k, right? This is k 0, 0, this is I, j. If you want to complete this, and then you can compute. Okay. So this will be equal to this. And then we also have the magnitude for the r prime is 1, or without square root, plus f prime x squared, right? And based on the formula that we have, then the curvature for this function of x is equal the magnitude of the f double prime x divided with this. So this will be, when you write 1 by 1, this will be with power of 3. Only write the r prime x cross r double prime. Then we write 1 by 1. So this will be f double prime x. And this will be 1 plus f prime x squared. And then we take the power of 3 over 2. So this is to say that we can also apply to regular functions as well. So if we have the, let's say the example, that asking the find curvature of parabola. y equal x squared at 0, 0, 1, 1, and 2, 4 points. I think you need calculators to calculate this. But let's say we are going to take this as this previous formula. Okay, so we have f of x. So we take y prime is 2x, y double prime is 2, right? And we take the curvature is going to be 2. It's already a constant, so we just take 2. And then 1 plus 2x squared, and then 3 over 2, so we have 2 over 1 plus 4x squared with power of 3 over 2. So we take the curvature at 0 is 2, okay? And we take the curvature of 1. So we take 2 over 5 with power of 3 over 2. This will, if you calculate the calculator, this will be equal to 0.18. And this will be 4,617 with 3 over 2. Or if you see, this is 0.03. So to observe this, we can conclude that at the point 0, the curvature is the highest. Okay. So if you see what this means, what this curvature really means, if you get the parabola, say this is the parabola. So let's say this is the y equal x squared. Okay. So from this computation, if we compute for all possible points of x, let's say this is 2 here. So the curvature will be like that. So if we want to observe, then at this point here, this is the change that is significantly large, right? From the negative gradient to positive gradient. So it's large in this 0. So that means in the curvature, we can also see that it is the largest value. Okay. So this is the y equal curvature of x. Okay. And as it's going to infinity, either the negative infinity or positive infinity, it will going to closer to 0, because the parabola, it tends to have a straight line for each part of the end of the curve, right? This is start to get vertically, this is also start to get vertically, but not vertical, but close to vertical. So that's why it's going to be nearly to 0, because the change for the vertical line is closer to vertical line is really small change, right? It means that it's really big change here, large change, significantly change here, but here it doesn't really change that much, right? It's the gradient is still the same. Okay. So you can think the curvature in the regular functions or in 2 dimensions, it's like a rapid change in the gradient, the slope. So we still have one more section. Actually, it's called the normal vectors, binormal vectors, and the torsion. But I think I will keep that on next week. Okay, so I will stop until here. And probably I will give you more practice on chapter 12 and 13 for this weekend. At least you can maybe try one or two. But if you already get the idea, I think still okay. You can skip that as well. Okay. Is there any questions?
It's in curvature. Yeah, they have winches now. They have everything as you like. I know you'd be jealous, you know. I need snow. Yeah, but you'll be
So any questions?
5 minutes.
Okay.
Não, porque eu me sinto mandando, não.
Yeah, for last week midterms, is the time enough? I mean, for the amount of questions, is the time sufficiently enough? Or the question is maybe if the time is longer, can you solve it? If still no, then it's not time problem. Right? Okay? But time means that you need to write, right? And it takes time. And then maybe some process with the law, right? It takes time. Takes time, right? So I mean, time enough is for you to write and then to process all the answers. Enough, right?
It was more than enough. I left her.
And you can think like, if the time is longer, like can you solve it? If still no, then the problem is not time. So you need to have more practice. Okay, we are going to have our feedback. Okay, so I will end the lecture up until here. So the feedback is